My name's Kieran Carroll. I'm from Canadensys Aerospace in Canada, and my colleague Alexander Brown from Queen's University, also in Canada, will be giving you a presentation today on the lunar lava tube scouting mission that we've been analyzing for the European Space Agency under their OSIP Lunar Caves Challenge program. This mission involves sending a lunar rover up to the moon to scout around pit craters to map out lava tubes from the surface of the moon using geophysical instruments, in particular a gravimeter and a ground penetrating radar. Lava tubes exist on the Earth, and they're very common in volcanic areas on the Earth. They're the results of lava flows that get roofed over. It's been speculated for many years that lava tubes may exist on the moon as well, based on observations from lunar orbit showing lunar rill features that are very similar to rills on Earth, but much larger than the ones on Earth. This leads to a speculation that lunar lava tubes could be much larger than lava tubes on Earth, raising the interesting possibility that they could, for example, be potential sites for future lunar habitats. But in any case, they'd be very scientifically interesting to explore. For example, they could contain pristine, unmodified material from billions of years ago in lunar history. They could contain lunar resources that couldn't be found elsewhere on the moon. Lunar pit craters abound on the moon. There are many that have been discovered in the past 11 years. The first one, the Marius Hills pit crater, was discovered by Haruyama from the Japanese Space Agency in 2009. These are potentially skylights into possibly huge lava tubes. And at the bottom right, you can see a skylight into a lava tube on Earth in Hawaii for reference. All the other images are pictures of pit craters on the moon. And there are other causes possible for pit craters on the moon. For example, they could be skylights into small impact melt ponds instead of extensive large lava tubes. Now, exploring inside of a lava tube would be most interesting. Exploring inside of a small melt pond, probably less so. A mission to explore either one of them will be complex and expensive. There is a risk in sending a mission to any particular pit crater to explore inside of it. What if the void beneath the pit isn't a large, interesting lava tube, but is instead a small, not so interesting impact melt pond? We propose sending precursor missions to one or more candidate lunar pit craters in advance of any sort of a cave diver mission to investigate whether those pits have extensive cave systems underlying them. We believe such precursor missions could be considerably less expensive than the subsequent cave diver mission. We propose using geophysical techniques to detect and measure the size of subsurface voids and their location using measurements made from the surface of the moon rather than having to go down inside the pit. We've examined two geophysical techniques that are very appropriate for this, both having been in common use on Earth for many years. Gravimetry and ground penetrating radar have both been used for terrestrial subsurface exploration for many years. And the results of these surveys could be used to decide which pit crater would be best to send a follow-up cave diver mission to. Next, my colleague, Dr. Brown, will describe the scientific aspects of this investigation.
Thank you, Kieran. I'm going to talk about the science study we conducted. We had several objectives. First one is a sensitivity study for rover-based gravimetry. And the second one is also GPR, ground penetrating radar, feasible to detect lava tubes in the subsurface of the moon. Then we also studied synergies between gravimetry and GPR and the survey design, which is highly relevant in order to minimize the number of stations and the path the rover has to take in order to sense the lava tube in the subsurface. Since we don't have any lava tube models from the moon, we took 4 Earth analogs. You see those examples here. And we created density models around those with regolith densities and basalt densities around those empty lava tubes. And those 3D density models we injected into IGMAS, a modeling software, which then translates density distribution into gravity parameters at those stations at the surface. From that, we modeled a variety of those lava tubes with different depths, different diameters, different density contrasts, and created a database of gravity signals, which in turn then we visualized with this MATLAB app, where you can see the plan view of the gravity signal overlain by the outline of the lava tube. Here in 3D, you see the gravity signal. Here you see the depth profile of the lava tube. And here you see the station coordinates, which were used to create that data set. You can change a lot of those parameters here interactively, and you will see immediate change in the images. If we take a spiral turn, a spiral path around this lava tube shown here in the middle, starting here, or if we take a rectangular path around the lava tube, starting here, we will see different times it takes to resolve the lava tube, as well as slightly different results at the end. So here we have already, we can see the lava tube in the spiral path, while in the rectangular path, we don't really see it that early. And at the end, we're not seeing it as strongly defined as here. So it really matters what type of path the rover would take. And that's what we can now model with this applet. However, we wanted to make it even more user-friendly. We wanted to develop more different opportunities to configure targets. So this is a Flask applet based on Python and Dash. We can select targets, simple ones or lava tubes. We can configure them in density, contrast, in depths, in diameter. We can configure the terrain, the most important corrector information, the noise generator in gravimetry, and we can design and configure the survey parameters. Then we take those options together and compute through this triple integral gravity values, which we then visualize in this dashboard. Here's some of these examples of these modules, simple shapes of lava tube models. Then you can change their density, diameter, and depths, and so on. Terrain configuration, you can create random terrain based on your information about the terrain. You can make this smooth or rough, or you can actually use a real DEM as well. Survey configuration is possible. You can pre-program a spiral path or a rectangular path, or you can actually click on this terrain plot here and select where you want to survey. And then the more white dots or stations you select, it starts to build up the gravity signal based on those stations only. And you can also manually modify them in this matrix here. So eventually we end up with this visualization dashboard, which contains all the different results, and you can interact, you can draw profiles across and so on, and change also informative parameters and recalculate things. We have used this applet then to calculate a couple of lava tube models with varying certain parameters. In this case, we have the Lagos lava tube with a radius of 15 meters. The depth of the ceiling is 30 meters. And no matter what, if we change the density contrast, the depths of the lava tube, or the tube radius, we're always above 0.2 milligal, which is above the sensitivity of the Vega instrument. Next is the GPR survey. GPR was used on the moon before and was successfully used. We're using some of their parameters for GPR Max, is the software which forward models the electric permittivity distributions. Lunar materials, regolith, basalt, and air, all are beneficial for penetration depths. So we expect larger penetration, much larger penetration depths than on Earth, which is actually very good to, to reduce the size of the GPR. We solved Maxwell's equation in 3D with the finite difference time domain method, which is implemented in GPR Max, and then can solve lava tube models crossing a lava tube in 2D, in line with a lava tube in 2D, or full 3D survey. However, it's computationally very demanding, but it also has the option to add noise of dielectric permittivity or variations mimicking inclusions or ejecti. In this model here, it's a 2D model with a lava tube here in the middle, a 5-meter layer of regolith overlying basalt. And if we send a 50 megahertz GPR antenna across, this is the results we get. We can see the top hyperbola is based on this reflector point at the top of the ceiling here, the lava tube. Then you have side reflector hyperbolas. And from the bottom, you see also this side reflection is stronger here compared to the other side. If you double the frequency, you can see a little more detail because the wavelengths are shorter. However, the important thing is that the amplitude has not been reduced, which is very beneficial for us because the higher the frequency of the antenna is, the smaller the antenna can be, which means it reduces the payload. So that is good news as well. In summary, lunar gravity surveys are able to detect lunar lava tubes. Vega specs are sufficient to achieve the required sensitivity. GPR is able to detect and characterize lunar lava tubes geometrically. Both techniques work on their own. However, a joint survey would lead to model improvements and de-risking of the mission. The developed tools allow us now to model any scenario of lava tubes on the moon, and that will, this allows us to assess many different scenarios for the mission, for which Dr. Carroll will now say a few more words.
Now that we've taken a look at the scientific principles underlying gravimetry and ground penetrating radar, we turn our attention to what's involved in deploying those techniques on the surface of the moon aboard small, inexpensive robotic lunar rovers equipped with suitable instruments. The first step is to carry such a rover to the moon's surface, of course, which would be done aboard a lunar lander, which would land near a candidate pit crater and deploy the rover. The rover would then drive to the area of the pit crater, making gravimetry and radar measurements around the pit. These initial measurements will be used to provide an initial indication as to whether their pit is a skylight into a large lunar lava tube or into some smaller void space. And based on those measurements, the remainder of the survey would be planned out in order to explore to find the edges of the subsurface void and map its extent, the path direction of a lava tube underlying the pit, that sort of information. The main instrument for carrying this out, the gravimeter, is one that Canadensys is developing, the Vega space gravimeter, which has been under development here in Canada for the past 5 years. It's at an advanced stage of development, technology readiness level 5. It is an absolute vector gravimeter. It measures the gravity vector, not just its magnitude, but also its direction, with no bias. And it's quite small, but smaller than 10 by 10 by 20 centimeters. It weighs just over 2 kilograms and uses about 10 watts of power. Its accuracy is quite suitable for detecting lava tube targets. As Dr. Brown presented earlier, the accuracy that we can achieve of measuring 0.3 micro-G RMS error in a 10-minute measurement is quite capable of detecting the sort of lava tubes that we expect beneath these pit craters. Ground penetrating radar has again been used extensively on Earth for many years for subsurface exploration. 2 GPR instruments have been sent to the lunar surface aboard the Chinese Yutu-1 and Yutu-2 lunar rovers, which were part of the Chang'e 3 and 4 lunar missions. These rovers explored for several hundred meters on the lunar surface using an instrument operating at both 60 and 500 megahertz, both relatively long wave and rather shorter wave GPR. The longer wave GPR being able to penetrate quite a lot deeper beneath the lunar surface. The 60 megahertz channel of the instrument was able to detect reflections from sources as deep as 300 meters, as shown in the radargram at the bottom right of this slide. The instrument is relatively compact at under 5.5 kilograms and consumes about 10 watts of power when it's operating. This level of performance is certainly capable of detecting reflections from the ceiling of lava tubes of the depth that we're expecting for associated with these pit craters. The final piece of the equipment puzzle is the lunar rover to carry these instruments. And here we look at some of the requirements for rovers that come out of the study that we've carried out and what can be achieved with lunar rovers that are in development at the moment and close to being deployed. The gravimeter takes about 2 kilograms, the GPR 5.5 kilograms of mass. So the rover would need that sort of mass payload capacity. Each instrument, when operating, requires about 10 watts of power. So that's how much power the rover would need to provide to the instrument over and above the power needed to operate the rover, of course. The speed needed in order to carry out the survey is about 0.5 kilometer per day. And the range needed on the order of 5 kilometers of driving over the course of 10 days. As far as getting data back to Earth is concerned, we reckon that 100 kilobit per second data link back to Earth via the lander would suffice for driving the rover and bringing back the scientific data. In our study, we've looked at 2 different options. One, a small rover, quite small rover, a nano rover as we call it, 10 kilogram class carrying only a gravimeter. Option number 2 would be a larger micro rover, a 30 kilogram class rover that would carry both instruments. And here I'll quickly look through the mission operational plan, an example mission operational plan for carrying out such a survey for pit crater in the Marius Hills region of the moon in Oceanus Procellarum, which is near the crater Marius. And here's a view showing where on the moon that is, and views from lunar orbit showing the Marius crater and the Marius Hills region. This is a volcanic region with many volcanic domes and rills throughout it, as can be seen in these lunar reconnaissance orbiter images. The mission target is the pit crater, the Marius Hills hole as it was first named, discovered by Haruyama. His conjecture is that Rill A in this figure has an associated lava tube at the end of it. And on the right-hand image, you can see a zoomed out view of that pit at the end of that rill. Zooming in, the conjecture is that the pit is a skylight into that lava tube with a size of about 60 meters wide in its largest dimension. The current best estimate being that that pit is about 40 meters deep. Earlier estimates estimated deeper. That's one question that remains to be confirmed. The mission plan involves first landing near the crater, not too near. One doesn't want one's lander to accidentally fall into the pit. We've baselined, say, 500 meters away from the pit. And next, to deploy the rover from the lander and drive to the near vicinity of the crater rim. Now, say that there is a lava tube beneath the pit. Here we've sketched in a conjectural lava tube profile that's consistent with the surface topographic features associated with the rim. What we'll first do is a quick circular survey close to the rim. Of course, not too close. The rim edge will have a slope, and we don't want to be so close as to be in danger of sliding down the slope and falling into the pit. But we'd measure gravity and radar at multiple stations around this circular initial survey, mainly looking for gravity lows to give an indication of the lava tube alignment. And for the alignment sketched on the previous slide, we'd expect that the top left and bottom right gravity measurements would be lower than the other gravity measurements. Next step would be to circumnavigate again at a greater distance out to confirm the alignment from the first survey. And then, if all is well, to proceed to do linear surveys transecting the expected alignment of the lava tube on either side of the pit crater in order to define the edges and extent of the underlying lava tube. With rovers such as the Canadensys nano rover and micro rover designs, we believe that such a survey could be completed within 10 days, which is to say before lunar nightfall. The distance is about 5 kilometers for the survey sketched out, and the speed made good for the rover in order to carry out that survey in that length of time is about 0.5 kilometer per day. To conclude, there are existing and in development gravimeter and ground penetrating radar instruments that are sensitive enough to detect lava tubes beneath the lunar surface. And there are rovers, lunar rovers in development in the 10 to 30 kilogram mass range that are suitable for carrying those instruments and that have enough range to be able to survey the area within 2 kilometers of a pit crater, and that have high enough speed to be able to carry out such a survey within 1 lunar day, confirming that scouting around a lunar pit crater to confirm the presence of a lava tube is quite feasible. Thanks very much.